Bem-vindos ao novo seminário do DRCC. Primeira coisa, esse seminário vai ser gravado, vai ser gravado em IFGW. O fato que você está aqui por embora significa que você deve ter visto a bem gravado. Então, quero que você permita. Hoje, nós temos a grande honra de Sudip Jana. Ele é originariamente da Índia, da Kolkata, mas fez doutorado em Oklahoma, na Oklahoma State University, e depois ele foi para o postdoc no Max-Planck-Institut de Física Nuclear em Heidelberg, e na Universidade de Heidelberg, como é escrito relativamente superior da minha, Instituto. Ele é um grande especialista da identificação da física dessa aula de fótons, que é, se você faz física de partículas 1, vai ver que os núcleos não interagem com fótons, mas se você faz física de partículas 2, você tem que apresenta, né? Mas você vai as coisas são mais complicadas. Please, floor is yours.
Thank you very much for the invitation and thank you everybody for joining. So, we can see each other.
I'm sorry. I always forget that there is the. Oh, you have it. Yeah. Yeah, perfect.
So, thank you everyone for joining. So, I'll talk about light from the neutrinos. There are two aspects of it, I will tell. Light from the neutrino. First is how neutrino can save light on nucleus. That is one aspect. And the second thing is that neutrino is immune to electromagnetic interaction in standard model. Unlike other matter fields, which talks to strong, like which is responsive to strong interaction or electromagnetic interaction, neutrino only talks about weak interaction. But still, it can develop electromagnetic interaction under certain circumstances, so and which is already established. So I'll talk about all these details. So these are the two aspects which I will discuss. So before going into detail, let's see what is our current understanding of neutrino oscillations in an answer. So first of all, we know that the neutrinos in standard models are massless. There is no right-handed neutrino in standard model. So neutrinos are massless. That's from the theoretical theoretical point of view, like we know that neutrinos are massless. But then neutrino favor oscillation has already confirmed by say hundreds of experiments, which requires or the consistent solution is that neutrino requires and mixing, which you can explain the neutrino oscillation. And you can write down because as you know, like neutrino produce like it's a paper eigenstate, but when it propagates, if you consider it in mass eigenstate, you can always write down paper eigenstate and mass eigenstate in terms of the PML. You have three mixing angles and one Dirac phase and two Majorana phase and the mass difference. So all these three mixing angles and two mass fittings have been measured with 3% precision. So these are the neutrino oscillation observable in three neutrino oscillation paradigm. I took it from Nufi. So this is our super understanding, or like that is the goal. In neutrino physics, in upcoming decades, there are several experiments are upcoming. So what are the things they are trying to achieve? Of course, like these are 3% precision. They are trying to address all these issues like with more like say delta CP measurement and other things. So here I list down those things. So the first thing is that still we don't know how neutrinos get mass. Then the second thing is that what is the nature of neutrinos? Whether it's Dirac or Majorana, that has not been also, there is no conclusive evidence or nothing like that. So the neutrino mass what are they? Normal or imparted? These are the questions like which we don't know. And which I want to point out also, which I have done with Manfred and Babu, like there is one interesting correlation we found. Because in standard model, neutrinos are left-handed. And you know in SU12, all the left-handed electrons associated with the charged electron. So we find that if you try to write down and like magnetic moment of neutrino, that also correlates with the associated charge electron magnetic moment. And you cannot like disentangle this. This is coming from the residual counterpart calculation, which I will briefly talk about. That there is one interesting correlation between magnetic moments of charged electrons and neutrinos. And also there are several anomalies that exist and so on, whether this can address these of the questions. So to like of course there are different approaches you can take to address all these questions. We are trying to understand whether neutrino electromagnetic properties, whether there is some robust correlation which can address some of these answers. So first of all, like how do neutrinos get mass? These are the references in the work with Babu and Manfred. We try to see in neutrino mass model, when you try to generate any neutrino mass model, as long as neutrino gets mass, neutrino gets magnetic moment. So it's one-to-one correlation. Depending on the mechanism, you have a definite prediction of neutrino magnetic moment. So that's the thing which we study, which I'll tell you in a couple of minutes. The nature of neutrino, Dirac and Majorana. Like Iago is there, I wrote two papers with him. Like in these two papers, we are showing like how if neutrinos are Dirac in nature and Majorana in nature, how it can lead to different type of signature if it causes some electromagnetic properties or electromagnetic moment. Because of the structure, if you write down the mass matrix for the Majorana neutrino, you cannot have intrinsic magnetic moment. That means mu alpha to mu alpha. The same Weber transition cannot happen for Majorana. But for Dirac, you can have that. So that will lead to some characteristic signal, which we will tell also or highlight that how it can tell something about neutrino mass already. And then as I mentioned, which is very important because nowadays like neon G minus 2 goes up. So of course there are some discrepancy from lattice and so on. Irrespective of that, whether anomaly goes away or stays, still it is important that charge electromagnetic moments indirectly can put a stringent bound on electromagnetic moment, or electromagnetic moment can put a bound on charge electromagnetic moments in an indirect way, because in standard model it comes into the same model. Okay, so I'll talk about that. So let's start with the following thing. As I mentioned, in the standard model, neutrinos do not have direct coupling with protons. You know that neutrinos interact via W and G bosons, but there is no interactions with protons, and neutrinos are massless. But in quantum loop correction, when you try to generate neutrino mass, immediately on the loop level you generate some neutrino magnetic moment. So you can write down neutrino mass and magnetic moment in a very simple relation, like one-to-one correlation. And as I said, like there are different properties of neutrino electromagnetic properties, say magnetic moment and electric dipole moment, neutrino electric charge. Even if we in standard model, minimal standard model, we assume that neutrino has zero charge. But you can write down, because in standard model there are 5 global symmetry. One Barian number, one electron number, and one electron number for each family. You can do a hypercharge field and still neutrino can have many charges. Okay, and that is completely anomaly. And that can be there in standard model also. But the fact is that it's highly constrained and other things, but from the theoretical point of view, neutrino can have tiny charge, and that is anomaly, and that quite consistent with the standard model. We identify in standard model U1 or U1 hypercharge Y, but that Y can be anything. You need to take a combination which is completely anomaly, so then it's fine. So these are the property neutrino can cause, but particularly the neutrino magnetic moment, which is an interesting one, because it's correlated with the neutrino mass. Both are same density. Okay, so now before going into detail, as I said, so to summarize, we quite often talk about charged electromagnetic moments, charged particles magnetic moment. That's a different charge strategy, because like you can think of like a racing car on a track. or in a powerful magnetic field, the same thing happening in formula. You punch mu on beam and it's circulating almost like the speed of light. Then after a few loops, it decays, and from there you try to see how much they rotate in their axis in a powerful magnetic field. That's the way you measure charged electrons' magnetic moment. But neutrino is different, right? You cannot do that thing for neutrino. So then how do we measure the neutrino magnetic moment? So just to give you an overview, of course I'll tell in detail, there are different ways of looking at it. One such example is that suppose from any source, whether it's sun or supernova or any other source, neutrinos are coming in, and whenever it reaches Earth, in Earth detector, suppose if you have neutrino magnetic moment, it leads to some, in scattering experiment, it leads to electron recoil or nuclear recoil. So in lab also you can measure such neutrino magnetic moment in these ways. Okay, let's summarize all the possibility where it can give some implications with neutrino magnetic moment. As I firstly mentioned, if you have detector in scattering experiment, any neutrino scattering experiment, and neutrino has magnetic moment, then you can compute that this E is the recoil energy of the electron. You can see that's the standard model contribution. But one interesting feature you can see in the neutrino magnetic moment is goes like 1 over P is the recoil energy of the electron, which you are looking at. So we can have any neutrino source, whether it's coming from sun, dark matter detector, or it can be accelerated neutrino in any other experiments. If you look for scattering, you look for electron recoil or nuclear recoil, and there is a 1 over P enhancement. What does that mean? If your experiment is sensitive to the lower recoil energy of the electron, it's take a sharp P if you have neutrino magnetic moment over the standard model diagram. So you can clearly discriminate the background very well. So that's why in any scattering experiments, that's how you can directly look for it. And also another fact I want to mention that all the dark matter detection experiment particularly ongoing, or any scattering experiment is ongoing in 10 years or 20 years, if any axis appears, always you can try to interpret in terms of magnetic moment or some electromagnetic property. And it's very robust because you know the neutrino flux. There is only one number which is affecting here, that is the neutrino magnetic moment. On the other hand, for dark matter and so on, like you don't know if it's dark matter flux, what type of dark matter, there are many this model, that model, and so on. But in any scattering experiment, as I said, like always you can try to interpret if any axis appears or anything appears in future, always you can try to interpret in terms of neutrino electromagnetic property. And that's very robust because that should be there. Then you can ask why it's so robust, because we know neutrino has mass, and that immediately tells you that neutrino possesses some magnetic moment. So that's why it's very interesting to look at this type of scattering things. Then the second thing is in astrophysics. So what happens if neutrino has such magnetic moment or interacts with photon like this way, a lightning star like red giant or horizontal branch star, this photon develops some mass which we call plasmon mass, like it's around 10 keV. And if develops some plasmon mass, via this interaction it can decay back to neutrino. Okay? So this plasmon can decay back to neutrino. And what will happen? So then the extra drainage of the energy will be faster. And it can conflict with the standard solar evolution model. So from that you can put also type kind of constraint on this type of electromagnetic moment. This is another place where you can look at. Then third thing, which is very interesting and which me and Iago we looked at, and also it was very quite popular topic during late 80s and early 90s, which I mentioned, that nature has naturally there are some strong magnetic field exists, like in supernova or in star mergers or anywhere. So if you have strong magnetic field, like when you consider neutrino and antineutrino propagation or evolution, you need to take into account this effect of the magnetic moment. Although it's this M is the neutrino magnetic moment, it's very small number. But if you have a very strong magnetic field, you cannot just ignore. And if you consider these two diagonal entries during the neutrino evolution, you will see that it will hugely impact the whole propagation. Like, of course, you need to have large magnetic field and so on, but you cannot just ignore. So this spin precision in presence of this magnetic field, like it's called spin flip transition and so on. And then you need to take into account for the neutrino oscillations, how you can impact and so on. You cannot just ignore. And the fourth place which you can look at, which is decay or Cherenkov effects. If your neutrino has such property, like one neutrino, like transition type of magnetic mode, then one state can decay to another and photon. And the neutrino decay is a tightly constant and it can impact in defined experiment defined way. Whether it's neutrino telescope in other experiment, suppose say when in common experiment, like this neutrino anomaly appears, like from the downgoing and upgoing there was some mismatch. Even if this was one of the explanations that it can decay and that can fit. But okay, over the time we have known that what was the reason, but like this decay or Cherenkov effect is also quite important. So here I just summarize like all possible way how you can look for the neutrino and photon. Also, I want to put some historical context that this Frederick Reynolds, who who discovered who first detected the neutrino, even first detecting the neutrino, he looked into this neutrino magnetic moment beforehand. Because he published later, still it was written that time it was called neutron, not neutrino. Later it was like in Italian some conversation, I think, small neutrino, so they put INO, neutrino, like. But this common generation Harrison, even before detecting the neutrino, or anti-neutrino to say, they look for neutrino magnetic moment because they thought that maybe neutrino has some mass. Okay. In 1954, as you see, and they were trying to look for magnetic moment for the experiment where they're looking for neutrino, and they took a limit of 10⁻⁷ movement. And that's the first study of neutrino magnetic moment which appeared in the literature. And then in 1963, there was a second paper which appeared by Max-Planck and other people, where they summarized that there was nothing new, but like they give a nice overview what type of electromagnetic properties are important. If we are trying to understand the neutrino, these are defined as elements and charge areas, neutrino electric charge and electromagnetic moments. All reactor experiment you need to be careful because if you have some larger magnetic moment, then it can impact all the experimental data. And then I put chronologically all these timelines if you see, and I can explain why this timeline is something like that. That during this time, late 80s, the solar neutrino problem arises, and people are trying to explain this solar neutrino data by this neutrino magnetic moment. So that time it was quite popular. So during 90s, there are defined reactor experiment, and all these experiments they are trying to look for this neutrino magnetic moment. You can see it starting from 92. And then 93, Rovno, Muno, Texono, Nema, and in 2022, FONAS also, which look for this neutrino magnetic moment. And also accelerator and solar, as I mentioned, maybe in dark matter delay detection experiment. Your background is kind of neutrino, but neutrino can have some new property, which can issue also some sort of electron or nuclear recoil, which can be confused with any dark matter axis. So, Geno Newton also put a type bound on 10⁻⁻12 whole magnet. So whole magneton unique, like you can see the timeline of all these experiments. After 54, then when solar neutrino problem arises, people are so excited about this topic. Even if I was mentioning that rate is in the Homestay paper, like still we believe that electromagnetic moment was a solution for solar electricity problem. So during that time, that was quite activity was ongoing. In 2020, there was some access appeared in Vietnam. It was one of the explanations. Of course, it's wrong, but in the perspective of that, as I said, it's a very robust property to understand mass mechanism, because how you are constructing your mass model is a one-to-one correlation. So before going into the model detail, the astrophysics and cosmology part, let's try to briefly summarize what are the consequences you can have if you have such electromagnetic moments. I briefly mentioned also that photons in the plasma, as I mentioned, photons in the plasma in any red giant or horizontal bright star, they develop it's called plasma mass. It's called medium dependent mass. It can behave back to neutrinos, and if you have an electromagnetic moment, it can drain the energy faster, and it will be conflict with solar radiation model. And this Rapid and company put the strongest limit on that, 10 to the power minus 12 volt. This is from astrophysics. That this limit is like 10 to the minus 12 volt magnetism. And also from cosmology, also you can have some, because it can contribute to the effective also. But this limit is quite not severe. It's 10 to the minus 10 volt magnetism is Kudar and Baha balancing and with all the detailed study this constraint. But there is one catch here which I should mention. In standard model, neutrino can decay to neutrino via these diagrams. Okay, it is important because we have to understand. Maybe in 2020, me with Babu and Namke, we proposed one mechanism that whether this how robust is this astrophysics mechanism, and whether there is any kind of loophole or not. So we call it neutrino trapping mechanism. What does that mean? As you see the diagram here, the photons or the plasma decay back to neutrinos. Suppose the neutrino also develops similar way some medium dependence. If neutrino talks to some ultralight particle, and in that stellar medium, neutrino also develops some. So this is you can take this. If neutrino also develops some, you can take its mass. It's mathematically not possible. You just this decay is possible. Okay. So as simple as that, then neutrino will be trapped. But there is some problem also. It's not so trivial in the sense that if you block this kind of decay, so then astrophysics bounds will not be applicable. Like from the activities you do not need to care about this into a minus 12 moment. But there is some issue also. If you see this diagram in standard model, then that will be also completely blocked. And that has some consequence also, which Rapid and company says that like within 10%, even if you block this diagram, if you affect on mu and mu tau, it's fine. But if you block, then it will be very in conflict with the standard picture. And here I just roughly mentioned that, yeah, so let me tell you like how you can develop this type of medium dependent mass. I will not go in detail. If your neutrino talks to some light, ultralight particles, and which mass is inverse side of the star, say R inverse, if you so then you will see that you can develop some medium dependent mass, and that's how you can follow it. And this type of idea, recently many people are working on it. First, like Stephen Parker all work on it, and Alexi and company also work on this with ultralight mediator and medium dependent mass of this thing. Yeah, so I'm not going to detail of that. Now let's talk about why we should study this electromagnetic and why it is so important. So look at this diagram. The magnetic moment, this is the diagram for electromagnetic moment, neutrino photon. We don't know how to say what is the new physics inside it because we do not have any new charge particle so far discovered other than the standard model particle particle exists. So, and they put a bound around 100 GeV. The center of mass energy was 290 GeV. So at least you see that these particles, some particles will be about say 100 degrees or so. And this is an electromagnetic moment. And this is the same helicity operator, which is neutrino mass also. If you remove the proton, you can write down neutrino mass in terms of the electromagnetic moment. There is only one unknown quantity, which is lambda, which is the new physics. So, if you know the new physics scale, which is generating neutrino mass, you know immediately the electromagnetic moment expression what you can get. Because all these other things are known. This is electron mass, and you are just normalizing with more magneton and so on. So that's what I'm writing here. In absence of additional symmetry, you can write down basically neutrino mass and neutrino magnetic moment have some very simplistic relation, like which is lambda square mu over 2 mu p. But if you put some simple number, say some 100 dB some charge particle which is also, that will be the best expectation you can get. Then if you put those numbers, like you will see that whatever the experimental sensitivity currently, like in the minus and if you see some access in next linear terms, in any scenario, I just do some bottom top approach type of thing. Suppose we see some events in and I'm trying to interpret in terms of electromagnetic. The sensitivity is around 10 to the minus 11 micrometer. And if I back calculate it, like you will see that neutrino mass will be 0.1. So it's 6 orders of magnitude with our current understanding, because you know this scattering other experiments already took a bound of say 0.8 dB or 0.2 dB, something like that. So this is in conflict with our standard expectation. It's a 6 order of magnitude like higher. So these are known as magnetic moment phenomena, because if you, so that's what I'm trying to put in a cartoon diagram, that if electromagnetic moment is trying to achieve the experimental sensitivity, it's also pushed down the neutrino. So it's one correlate. Okay. That's the same thing I just already mentioned that 3 decades ago, like when the transport activity in the chlorine experiments, these experiments when it was appeared, it was quite popular. And people are trying to do this filtration transition inside solar magnetic field, and such transition would even undergo matter resonance resonance. That was a proposition done by Lee Marciano and Ahmedov in 88. And it was quite popular, and during that time there are very significant theoretical activities that address this about the compatibility of these large magnetic moments with small mass. And but after that, in the theory side, there was not such result. There are many phenomenological studies that have been done, like looking at different study experiment, what could be expectation, and so on. But it becomes very relevant today. Looking at the, if you see that different experiments are upcoming, whether it's oscillation or scattering, like it becomes very relevant. If any anomalous event appears or anything appears, always we need to keep an eye. Maybe there could be something of mass becoming from this type of electromagnetic moments signal. And yeah.
So this result was appeared or what? Not already.
So no, the result, whatever the observable of some sort activity still is there, but electromagnetic moment has some different expectations. Solar magnetic field is not enough to have this spin decision inside sun. Let me put like this way. So you need a huge large magnetic moment which can do this thing and affect the standard oscillation. But it will be there, but you just don't know at which scale it can affect because of the solar magnetic field.
So they are not the experimental anomaly is still there, the anti-correlation is
yeah, there maybe Orlando can tell me about it. So
there's some energy correlation, but it's very now to see on
okay. Okay, then enough.
yeah.
Okay, then just continue.
Yeah. So, but like, irrespective of this anti-correlation, up to snow experiment or Cromland experiment, still the solar neutrino deficit you can explain in terms of the magnetic. The reason is that if you have new producing and it's new going to say new bar or new tau bar, and it oscillates to other states, then still you can explain the deficit. And until I think snow result, like snow collaborations result, it was well consistent with the data. Even I heard from Alexi that it was giving much better heat than the standard MSW solution. But then it was refuted because in normal experiment you like particularly see the oscillation pattern, and also another thing in snow you have kind of three system equation where neutrino is talking to the heavy water, and you can literally this system get charge line interaction and neutral line interaction. So you can have a total expectation of neutrino flux. Because you need to remember standard MSW happening between neutrinos three flavors. Okay, but this neutrino magnetic moment happening between neutrino to anti-neutrino. If you write down 6 states, 3 neutrino flavor, 3 anti-neutrino flavor, it connects between neutrino to anti-neutrino. So it's a different kind of expectation you can. Okay. So anyway, so now let's see, because I am telling, like as I said, show the broader picture that neutrino mass and magnetic moment both based on some simplistic diagram. But if you then work out in very simple models, like say, okay, like the other charge fermions, how you get mass. If you just immediately introduce right-handed neutrino in standard model, you can get neutrino mass, and there is no problem. So you have just U power very small. Even in those cases also, you have a standard expectation. Your magnetic moment expectation will be quite determined. Let's look at this thing. So this is a simple diagram. As you see, the neutrino going into the W, and as soon as you put the mass insertion, because it's a very significant operator, it's a new L to new R transition, then you can write down electromagnetic moments in this standard model class in one type of scenario in terms of neutrino mass, which is worked out by Fujikawa and Stock in 80. And you see that in the standard model, at least one species of electromagnetic moment should be residual minus 12 moment. That's the expectation. But there is some catch. Of course, like if you are clever enough, you can construct some, because here all are left-handed currents. So there is no tidal insertion, like tidal insertion happening inside. Okay. How it can be advantages, like let me try to explain. So in this type of diagram, since all currents, like all the neutrino, electron, all are left-handed currents because W, you will have a neutrino mass there. But suppose if you have some different symmetry theory, I want to avoid this neutrino mass insertion rather than I want some tidal insertion inside the region. You can do that. You can do that when you have a right-handed current. Like you are basically writing mu L to LL by WL, then WL, WR means, then if you have right-handed current, you can have a tidal insertion inside. Okay. And and what it can lead to, then if you see the neutrino mass will be replaced by charge electron. Because you know in this type of blue diagram, if you compute, like you will see that wherever the tidal flipping happening, that mass will be proportional to this magnetic moment expectation. So here you can see that you can expect something from enhancement of charge electron mass over neutrino mass. So neutrino magnetic moment expectation can be quite high. That's from the simple argument you can see, but and this also worked out by several people. But this is also tightly constant because of this WL WR mixing. If they do mix quite huge, that needs to be US gamma and beyond affinity and so on. And if you in current status is like it cannot be better than -10 minus 15 moment. Even if in some optimistic scenario, you can see like it's 10 minus 15 moment.
Sorry, what is the last fraction?
Left side difference between the two? You do not have any WR. So there is another issue. Like you have in standard model, is 3 color cross, is 12 cross.
Okay.
But in left right, you have 3 color cross, is 12 cross, is 2R crossing 1 B minus. So you have a 2-stage breaking. It's 2R crossing 1 B minus, and the next is 2R C11 and then
What's the mass of the bar?
It's currently like 5 to 60 people, like 14.
So it's not the same as the usual.
No, that's quite obvious. That's what I'm trying to say. So you have acidic color, acidic electric lighting. You have the first step, you will make these two to U1Y. And that's happening via something delta R or something, whatever this gets there. And then if you have, at this stage, you have rectangle one and then you are taking down U1 by this kind of one. Like there is some very tablet. So you see like this breaking happening at the high scale. It's a two-stage breaking. If you have refractivity, also this comes from some bigger things, say sodium or some Parkinson and so on. So if you break down through, it's the refractivity theory. But similar to well, you have a right-handed current, you have a similar to W boson, you have a right-handed W boson. Similar to J boson, you have a right-handed B boson. But since you are breaking it at a heavy scale, it's getting some heavier ones. Then you are breaking it at electronic scale. You see all the J bosons here in the say 100 dB scale, but these are in dB scale, like or it can be more higher and so on. And the current bound is around 400 dB.
And this combination is not suppressed by the heavy scale.
Yeah, of course, it's a hit, like whenever this mixing you consider, this mixing would like if you can think of the this is a case kinetic term, like mu pi beta mu pi. So basically, if you expand it, you can write down this there goes some mathematics, a W and W are basis you are writing, you will write some say the mass square matrix if you are writing it will be G square V L square, G square V L square into 2 and 1 2 and 1 will be G G prime is G L G R P L D R combination of two things. And these two terms admits these two states because we don't have order. And of course, whenever you write down mixing terms, there will be the denominator, there will be some area scales in this software. Of course, that should be there. So, okay. So I'm not going to too much detail, but in this way, you can systematically work out all different class of neutrino models and what type of expectation you can have. The same thing you can do for supersymmetric theories also, and you can write down like what is the expectation if you have some alternating breaking interactions, and all these cases you will see that these numbers are quite small, in the minus 15 over. And by the way, then you can ask, okay, what about our favorite seesaw models or the simple like that's I think I can do here and write down one master. What is the expectation of those models? In this favorite seesaw models, even if these numbers are quite like restricted for the transition magnetic moments. This should be like around 10 to the minus 23 more magneton work out by Paul and Wittgenstein and so on. The reason simple because for the electromagnetic moment matrix for the Majorana case, all the diagonal entity if I write mu alpha beta, alpha and beta supports a defined way, but if you write it down mu beta, so all the diagonal entities are zero. But for Dirac cases, there will be a p on this side. So for Majorana case, you can have say mu equals to mu and gamma. You cannot have mu equal to mu e gamma. That's from the Majorana nature if you write down. Because it will be like this particle is energy, muon antiparticle. If you have magnetic moment, you cannot write down such things, so diagonal terms will be zero. So, so for this type of expectation is 10 to the minus 23 more magneton. Then we zoom into detail whether there is some like nicer way you can disentangle neutrino mass and magnetic moment. Although the operator you write down neutrino mass and magnetic moment, those are both are helicity fitting operators, but there is some fundamental difference in the Lorentz structure. One scalar and one state. So based on that, we found two mechanisms. One is called spin symmetry mechanism. I don't know whether you guys are familiar with, they are called popularly known as bar graph. Whenever you compute some charge electromagnetic moment, this type of two-loop graph might appear in the IFGW model, superconductivity, and so on. You need to take into account. Sometimes this type of two-loop graphs becomes more dominant than the one-loop graphs for electromagnetic moment calculation because of the reason that you need some two-pile activity to reach to do. So there is one nice idea like how to disentangle this neutrino mass and magnetic moment. What is some things I don't know. First is that like this was first proposed by Barkley and in 1990. That in Shannon model in the normalizable base theory, there are no direct coupling gamma WS. So this type of gamma, a spin 1 particle, sorry, spin 0 particle and spin 1 particle, in 3 level you cannot write down such interaction in the laboratory. However, in loop it develops. But the thing is that if you remove the photon, this type of spin 0 particle to spin 1 transition, it cannot occur. It's weird, right? So if you remove the photon, the spin 0 particle cannot just suddenly happens to the spin 1 part. It doesn't happen. So as for its contribution to nu for transversely polarized vector motion, that's what I'm writing, that spin 1 to spin 0 transition can occur. Only the longitudinal mode, the Goldstone mode, will contribute to such transition. So in this type of mechanism, they call it spin symmetry mechanism. Then in 1992, like this guy, like they talked about spin symmetry that if you have such two graphs where you are involving this type of photon spin 1 spin 0 particle interaction, using that you are getting large magnetic moment that doesn't significantly contribute to neutrino, or it doesn't offset the small neutrino mass. But the model was quite complicated. In 92, then later they mentioned about using it in G model, simplest, one of the simplest radiating neutrino mass model. You can achieve that, but they never computed this diagram. Then in 2020, we worked out all these possibility whether we can still achieve the magnetic moments defined by the graph, and we worked out all the possibilities. You need to like keep in mind one thing, that all of these diagrams looks complicated, but it's limited possibility. The reason is that you start with LL, there should be somewhere deep 6 insertion, because as I say, electromagnetic moment is very significant. There should be some 2 electrodes involved somewhere in the loop. Either this can be insertion here or in this vertex or anywhere it can. So there will be LLHH operator you are writing. It's not like you can escape from the very high magnetic moment. So I'm not going into detail, but if you have some questions about the calculations or the models, how it works out, and you want to learn about how we can deal with these problems, because you see, whenever you do, like you can have some electron hadron facility from the neutron interactions or some collider implications in RLH, and we find that in very optimized data, no matter what model you do or n number of doublet you extend it, as I say, at the end of the day, effectively you might be right now which is type of operator. Using that, you need to build up the answer. So we find that you can maximum achieve the minus 12 lines. Then the second and another interesting independent mechanism which can disentangle this mass and magnetic moments, that we call like horizontal symmetry. The idea is very simple. As I said, although like both are same helicity fitting operator, one is Lorentz scalar, the mass operator, and the magnetic moment being a Lorentz tensor operator is antisymmetry in the two family. And in 88, Holocene rightly, like, very nicely identified this idea that if you impose some SU to new symmetry, because their order structure is different, if you have some SU to new symmetry, or neutrino transforms into unit conjugate, then it can contribute to neutrino-magnetic moment, but not to neutrino mass. So that's the idea that's popularly known as Boltzmann symmetry. A neutrino mass term in symmetry under this extent will then be forwarded by SU to mean symmetry, while the magnetic moment operated in anti-symmetry under the extent. Then the later year, like after Boltzmann proposed this idea, actually Barbieri and Mohabbat was trying to whether there could be some unique on some of that, like whether they can really write down some mass model based on this. But they found that it's quite complicated and it's almost impossible. And the paper's conclusion exactly is that. Because the reason is that this is hard to implement this Boltzmann symmetry because they have done community to stand up. What does that mean? Like you develop some charged electrons, like kind of Majorana type of mass terms, and it doesn't respect the standard model, so it doesn't only the standard. So that idea, if you see rather than SU to new symmetry, which is Boltzmann symmetry, which is transforming new to new conjugate, to horizontal symmetry. How does that work? The same idea, but you have three flavors. If you have two family symmetries and around two flavors, so that's what we are doing. A horizontal symmetry acting on the electron and muon family can serve the same purpose as such a symmetry commutes with the integers. And it doesn't have any problem. So that's called the horizontal symmetry. And we very simplified scenario we take. The symmetry was approximate broken explicitly by electron and muon mass. And this is analogous to parallel symmetry working in the strong interaction sector by mass of the light ones. And this is the model. But don't be scared. There is no extra Fermi. These are all standard model Fermi. Just you are defining such a way that these are the SU2, the new symmetry charges. There is no extra Fermi. These are like first family and second family are constituted by fundamental. Like that's how you are writing because you have SU2 charge 2. And also for the electron and muon, that's how we are writing, and the tau super suppose say this one. So then immediately what we need some scalar sector to be there, which is taking the electron number, and then we find like almost like in the model type of spectrum where SU2 acts horizontally and SU12 acts vertically. You can disentangle that. What does that mean? Disentangling, like there will be two diagrams, like for electromagnetic moment. Due to this SU2 symmetry, if you compute this, you will see a relative positive sign will appear. But for the neutrino mass, due to this symmetry, automatically it comes with a negative sign. For the neutrino-magnetic moment, it will enhance, but for the neutrino mass, it will be exactly like 0. Of course, whenever you are breaking this symmetry, it will be tiny neutrino mass will be generated, but that breaking is going like a square because you are acting on the electron and muon families. It will go like L square minus L square equaling to it is two surface. And that is not affecting your current understanding of neutrino mass. So in this type of scenario, you can it doesn't respect electron number, but another interesting thing is that like in this type of a model, like in horizontal symmetry between say first two families or second third family, like it respects electron number. So it respects the L minus L symmetry or L minus L tau symmetry, depending on what type of symmetry. So that will not allow any significant electron field of R's. It will automatically. Okay. So here that we are showing that for this type of scenario only, if suppose in future you see some like some accesses which is consistent with electromagnetic moment, you need to come up with such symmetries which cannot upset neutrino mass but can give significant neutrino magnetic. So these are the two ideas as I mentioned, and this is kind of a global picture I'm trying to show that let's look at the different models we are aware of. The seesaw model or standard model plus right-handed neutrino or some mini-charge particle or left-right theory or SUNY or spin symmetry or horizontal symmetry. As you see, and this is the electromagnetic moments number value. in late 80s or early 90s, there was a sensitivity which was solving solar neutrino problem. And currently we are here in Gen term, which is 2022. You see, there was almost like 5 orders of magnitude completely open. If in future experiment, any experiment see such accesses or anything, you do not have basically neutrino mass model just okay, so in the other way around, like it will be also kind of interesting. Like I'm talking about one particular idea, right? Like how looking at neutrino electromagnetic property, we can say something about neutrino mass mechanism and so on. So it's interesting to see that, like in 5 order of magnitude is completely open. Like from here to going here, it took like from 90s to now 2020. So of course we don't know what technology development will be happening in 30 years, what type of sensitivity you can go up to. But you see, it's high time to look for still waves and maybe like try to look this mass, not upsetting the mass within getting some like electromagnetic moment happening. Okay, so far anybody has questions, because I will just now briefly so how much time is this there?
It's 50 minutes,
Okay.
but it's sort of a softball, put it this way. Yeah, I mean, if you want to continue for a little bit further, people need to leave, they're ready to leave. But,
Yeah. Okay, I'll wrap it up in 10 minutes also. So,
yeah.
okay, let's continue then. So far we see that. So let's put it like this. What so far we summarize? Neutrino oscillation has been observed, established. That requires neutrino mass and mixing. And if you require neutrino mass and mixing, that demands neutrino had magnetic moment. As simple as that. So that means neutrino had magnetic moment. Now I just discussed in different neutrino mass models how it can be interesting, like depending on the mass mechanism, electromagnetic moments can have defined expectation. So that's why it's a very fundamental property. You can, if you establish electromagnetic moment strength, you can somehow indirectly or directly like say something about the neutrino mass. Then another interesting aspect which I find, or which I found with Babu and Manfred and on postdoc from Booster, that if suppose say you have electromagnetic moment like this, mu to mu gamma, I don't know what is physics inside it. If you replace its partner in SU12, the doublet where neutrino resides in, just if you changing mu to mu, you will say that the inside the loop also, whatever is appearing here, that's a SU12 partner will appear here. And we know that you cannot split these two particles too far, because that from the T parameters of the electron rho parameter constant, you know that that will be almost in the same scale. So that's what it is happening. Just one example I'm showing it here. So mu to mu gamma, suppose in a complete model you are writing it down. If you change mu to mu here, the residual partner, whatever is appearing here, that will contribute, its partner also will appear here. And since the chiral is being happening outside, you do not have any control over the sign. So these two u power, it's appear like mod u power square. So either you can give wrong sign or right sign. It's not like other theory where suppose if the tripping happening inside, you have to define u power. You can change the sign and say that, okay, I'm explaining 1 minus 2 and so on, whatever you need. But here, you do not have any control over it, because the current will happen outside. So you can literally write down electromagnetic moment and charge electromagnetic moments in 1-to-1 correlation, because of this fact that in standard model, there is no right-handed neutrino. If you say any model, that's what I'm writing, the model that you use electromagnetic moments, while maintaining their small masses naturally, also predict observable shifting charges from the. And that's immediate conclusion we found. This is, we are showing some neon minus 2 prediction with some reference numbers. and this is neutrino magnetic moment in two axes. And in this model, like in the horizontal symmetry model, we think that there is no control, like the 4-parameter space predicts some particular pattern of neutrino magnetic. And these are the numbers which we can take some undefined experiments or astrophysical bounds are. And if you see the neon G-2 current status, VNL was here, formula, experimental leverage, and this was the standard model prediction. If you take lattice into consideration, it's a different story. Okay, there are, you can see that like it's rightly explain the neon G-2 also, where the electromagnetic moments, 10⁻12 moment, and so on, which are experiments going to. It's kind of without doing any tuning or anything, it's automatically predicts. Let me put now my pessimistic approach. Pessimistic approach is that suppose the neon G-2 everything is correct and consistent with now standard model, okay, that can be also possible. So then you will reach to there, and that will put a immediate imposition on the electromagnetic moment constant that can, like you are looking for neon G-2. On the other hand, you can directly put a limit on the neon electromagnetic moment, or electromagnetic moment involving neon, which is 10⁻13. This is very interesting fact which we found, and we don't know like what is going to happen, like what is the value we will see, like this issue should be settled and so on. But it's an interesting observation that charge electromagnetic moments are one-to-one. Okay, then briefly I will summarize. Let's move the topic a bit. That the number or sensitivity which I showed, that's up to 10⁻12 moment, the scattering experiment and so on. Then the next question will be, if this property is so robust, so interesting, and one of the most robust evidence we found in oscillation that predicts this type of electromagnetic moment, why we cannot go for some interesting testable signature, or whether we can come up with some interesting aspect like which can prove some higher value, because if it is so robust, maybe we can say something about some different mechanism. That's the question we are trying to address, and I will not go into the this four-color supernova theory. The basic fact is that, which I earlier mentioned, whenever from the four-color supernova like galactic supernova, you need to consider this neutrino and anti-neutrino evolution. And you generally write down this matter potential, but in presence of this electromagnetic moment, you will have some of diagonal term, which you are writing down here. If you are to give Yago and Manindra. But although these are proposed in by Evgeny Kutama and RDA, but we try to see what will be the consequence in upcoming experiment like June and hypertrophy. We found it will need some new resonances. In addition to the standard NSW resonances, like it can lead to some new resonances which will alter the picture. And so if your electromagnetic moment is zero, because all these new will be like oscillates into other papers or other, like then you will see some sharp deficit in the flux in human and hypertrophy X-ray. And that's how we will measure up the electromagnetic moment. And here I'm just summarizing the picture that these are the scattering experiments, and if you consider new hyperthermal in some conservative scenario, even it can go up to 10⁻13 or 14, which is very interesting to look at the spectrum and so on. And this is for the Majorana case, but immediate thing you can ask for the Dirac case. Dirac case scenario, for the left-handed case, you have matter potential. For right-handed neutrino, you do not have matter potential. There is zero from the two whenever you talk about the neutrino evolution. But this is not zero already. So that means that I cannot see any new resonance with Dirac frequency inside the surface area. But we found that, like, if your magnetic field is like inside the supernova, like it's a kind of twisting in nature, it can create some like extra phase which will appear here, and then that can lead to some new resonance feature. So this due to distribution magnetic field features like near Yago which appeared here in last year. So we found some new resonances due to this type of the distribution nature of the magnetic field. And this is some kind of simplified picture I'm showing that whenever neutrinos are coming out, say MSW, two resonances are happening here. If this new resonance is happening, we find that there could be some resonances happening even before that. So if it happens, so that will change the whole picture. Like you need to take into account all the mu and tau evolution properly, taking into account this type of new resonances as well. So because their magnetic field is quite high, even if there is some lower limit of this, like in your 7 volts, right?
9 volts.
9 volts. Even if like you cannot go below 9 volts. So that means it's a huge magnetic field for this. So which will put this kind of resonance to be much more probable than the sound signal. Because sound is like say 1 watt or say maybe 1 to 10 watts or something like that. But here is like say 10 or so magnitude higher. So even if a small number can be magnified and the new resonance can show up. So that's what we looked into, and immediately we find that some interesting temporal spectrum you can find in the new and hypercommutative spectrum, and which will tell about this. Even if we did for millisecond, as far as I know, that new is targeting for nanosecond sensitivity. So this is quite important to look for this type of property in upcoming oscillation experiment also, like maybe that can go this type of electromagnetic moments. Okay, I will not further discuss these active to sterile transitions and so on. Maybe one thing just I will quickly say that the whatever I so far tell, like about all standard model neutrinos, no any sterile neutrinos or anything. These are just neutrino has mass that which neutrino has to be magnetic moment, all are active neutrinos. Even if you can have some active to sterile neutrinos, which generally like this active neutrino to sterile neutrino, that is like this is called active to sterile transition magnetic moment. That can also happen. You can look for defined experiment like phasor neon and so on, and it's going to do some electromagnetic required. I'm not going in detail. And also in the neutrino telescope, like you know that the UV cosmogenic neutrino flux, like which is representing new energy from here. We ask the question that okay, suppose if you have a sterile neutrino, we always try to address how light it can be. But then with Manfred and Warner, we are trying to ask how heavy it can be, like which can be proved in experiment. Of course, the answer will not be collider. Collider 40, suppose is now ongoing. But suppose it is a electrophilic in nature, I cannot produce the collider so efficiently. But in neutrino telescope, you can. So you will have some flux, and if you have such type of transition, we find that even if you can go up to say this grand infinity poema, this type of neutrino telescope, they can go up to 100 degrees sterile, which they can look for from the flux atmosphere. So, which is quite interesting, and I will wrap up with these slides that I so far talked about neutrino magnetic moment and its interesting correlation with neutrino mass. So, whether it's from the theory side or the testability side, it's very important and interesting to look for these, like what are ongoing, like you look at different signatures, even if say LSM in short baseline anomaly there are. If you really try to interpret with that in terms of this active visualization and so on. So anything can be possible. We need to be open-minded and it can open up anywhere. But there are other properties also which I have not mentioned. Like I briefly mentioned that in standard model we can write down some mini charge of the neutrino, which are like there are a lot of consequences of this, like charge conservation in like physical consequence of charge atom and so on, and other understanding is understanding we want electron charge, which is too small. But understanding that from a theory point of view, can have any charge, this can have some impact, but these are nothing to do with mass. You cannot anything left during the sun or anything like that. And also neutrino charge area and so on. So this is the summary. Theoretical and experimental investigation of neutrino electromagnetic interaction can serve as a powerful tool in search of fundamental theory behind neutrino intelligence. Second thing, which is quite important, electromagnetic properties of charged electrons and neutrinos can be correlated. And we also, in Tiago, we should find the Dirac particle causing large magnetic moments that new resonance effect is present. We find it so far the most optimal opinion we can look for to unveil the scenario. Thank you very much.
Any questions? Alguém perguntas? Vamos.
That's why usually in the beginning of the like the right it's a magnetic moment. But the also that I think there's a lot of driving so we charge leads no in all the modes where you have charge leads you should have magnetic moment for the thing.
If you have charge peaks, and that talking to electron and neutrino, in one way you can have depending on the nature, suppose say electric. So the charge peaks where it leads to electron number variation, you can have. But only charge peaks without electron number variation, you cannot have any diagram which can reach minus. So because you are starting with this splitting operator, which leads to this splitting. Also in G model, you can do that. I can draw the diagram. So to start with, so I will like this is Mahana, so both are going inside or go outside from the balancing. So let's do that charge 60. So you is going to area with the class. So this is doublet contracting in something here. But this is doublet. I need to have some R because this is the mass insertion. So that's where it's goes. So you see this is doublet, seeing that means I need a doublet. So this should be a defined particle which is doublet on the distributor. So then you can have it to be doubling. So this is the air level instance of operator. Which is generating the mass. So the same can be many photons from the charge from there or from the charge here. It can be nothing. But if you do not have such type of electron number value in down, particular can from electron number, you cannot write down. So that's very good.
I have a sort of a general, I mean, most of your talk are talking about the conundrum, where you basically say that the mass and the magnetic moment should go. But I mean, I don't see the experimentally there is no conundrum, because in theory they should be comparable, and in experiment they are comparable, in the sense that both are valid in any direct search. Up until now, it's consistent with zeros, what's wrong.
Yeah, but it's not due, right? You have a expectation of as some even if you are putting something to satisfy the neutrino oscillation rate, standard expectation is 10 to the minus 20. Okay, it's not due.
Yeah.
So even if it's
But just to say, I mean, the coupling constant, if you interpret the mass as a left-hand, right-hand coupling constant, and the oscillation as a flavor, these are dimensionless numbers. So the renormalization group running should be okay. I mean, they're small, they're not zero. This is the standard model, so anything tiny enough, it's whatever it is.
You see, standard model there is no neutrino.
Okay.
It's exactly zero. But if you add right-handed neutrino, you have neutrino, and there you will have a definite prediction of neutrino. You can write down that's a finite contribution, and you can run it. But as I said, of course, I agree that there is no such hint of electromagnetic moment or anything. Why I should rely, but I just try to show a defined approach of like,
If there is one, there is.
yeah, because otherwise,
There is one, there must be.
because otherwise people will write models and models of neutrino masses and we will not have any clue. What is the point? Like if there is some fundamental property which we can like first look at and tell something about the inherent symmetry of the model. So then maybe then you can zoom in particular those models which can predict these neutrino, right? So that's a different approach of looking. Of course, I can do another approach, like I build a model, I look for its signature, and you can do it. But confirm that that's the coming from that particular theory. It will take ages because there are many other models which produce anything.
And actually, in another, like in your last statement, you talked about Neutrinos part.
Yes.
Can you go to that slide for a second? Just to understand. Yeah, here. So, just from a sort of purely theoretical point of view, are you saying that if the neutrino as a magnetic moment, in general, you will have an anomaly in the charge?
No,
No.
I'm not, it's completely no.
Okay.
It's completely incomplete.
Okay.
I'm just saying it's also another property which leads to neutrino interaction with photons and which is completely different from electromagnetic moment. But it comes from the theory you are writing down. Suppose say if you are in the standard model, you want y, if you shift this, if you do not identify that at the hypercharge, rather than some shift of say, you can write down standard hypercharge. So something, this is standard hypercharge, how we define sometimes alpha, obviously, either define alpha in or beta alpha. So this alpha will take EG. So that's leads to neutrino exactly that zero charge. But if you put some alpha very tiny number of this is consistent, this is another from the theoretical point, like the molecular.
Okay, so it doesn't mean that you
Yeah.
Sorry, further questions?
You mentioned briefly in the beginning about Cherenkov radiation from neutrinos. I think it's a very nice question, but I would expect that the constraints coming from this kind of phenomenon would be way stronger than the scale would be the velocity of the particle, right? The Cherenkov
The decay.
Yeah, I think it's in the first slide or the second slide, maybe.
Yeah.
Can you explain a little bit more about this Cherenkov effect distribution?
So this one,
Yeah.
So please go ahead and continue.
Yes, but I think it's really what you were saying because neutrino travels basically at the speed of light. So I would expect that you have in polar forms. So I would expect that this would be a very strong constraint.
You are right, that will put some strong constant. Meaning if you, without current understanding, you put in the -12 volt magnet, you will see that this decay lifetime is quite large. It's very large. So it's time constant. We put some time.
About the relation between the magnetic moment, the free mass, and the mass of the new scale. You also have a calculation, right? Which would affect this relation.
Yeah, so you can absorb this C over lambda, suppose in one scale, and just telling it, say, so suppose you are writing down, and you are right, there is a scale involved, which is the mass scale, as well as a coefficient which you are writing down for the operator. You are talking about the involving coefficient. And defining the whole C over lambda as a one parameter, let's try to see what is the scale, say, for seesaw scales of the scale. That comes out to be 14 dB in mass. That sounds like C over lambda. Now you can define how what your C means or what your lambda scale is. You know, scale have changed.
When you talk about the connection to the charged electron, you say that the limit, so by if the terminal is correct,
Yeah.
and the result now the limit is correct, then you can put a constraint in the magnetic. So you said like 10 minus 13 or magnetic.
Yeah.
So but in that it can be at most 10 minus 13 or
Yeah.
okay, so not.
Yeah, no, it can be smaller, but yeah. So, but no, whether formula is correct or not, like formula, whatever formula observed, that's a number. It's about lattice calculations and the distortion calculations. Whether they agree or not, they do not agree. So if because whether it's formula or DNL, that's a experiment in hypothesis and particle in there. So there is no problem. The problem is that we have three contributions. Usually like the dominant contribution, electromagnetic contributions, then weak contribution, and usually contribution. Electromagnetic contribution you can decidedly do by hand also up to 5 million. That is very high. Okay. Weak contributions also everybody agrees that is the. But when it comes to hadronic contribution, usually contribution, that's where no human brain can do by themselves. We need something. So there are two approaches to do it. One is dispersion method, where you take for the Babar and all the experimental data and then you can interpret what is the hadronic contribution to this. And then lattice usually needs to be disabled. Okay, so if suppose lattice is correct, even at the end I will say that what is that leads to say but if it is this person so then we are finding that it's giving exactly the borderline of the minus 12 line, which is explaining the minus 12. So, and we do not need to do